All right, chemistry, let's take a look at our video lecture for Chapter 7, Section 3. We're going to be using chemical formulas here. Now, as I read these objectives, I want you to note that a lot of the things that we're going to do in this section are things that we've already introduced back in Chapter 2. We called them crosshairs. We called it conversion factors. We called it dimensional analysis. We called it the factor label method. Okay, we're going to be doing converting. So when some of this stuff sounds pretty intense, we're simply going to be converting between one concept to another. So what I want you to be able to do at the end of this section, calculate the formula mass or molar mass of any given compound. I want you to be able to use molar mass to convert between mass in grams and amount in moles of a chemical compound. I want you to be able to calculate the number of molecules, formula units, or ions in a given molar amount of a chemical compound. And then I want you to be able to calculate the percentage composition of a given chemical compound. So here we go. Now, formula mass is the molar mass of a compound, right? Of a compound. The molar mass is the mass of the atomic mass units of one molecule. This takes into consideration the number of atoms of each element in a compound. The formula mass is calculated the same way as molar mass, except it's measured in AMU instead of grams per mole. Again, this was a point that we really tried to hit in Chapter 2 and Chapter 3. So if we need to refer back to one of those videos, we can. But for right now, we're going to move forward. So this is something we should be able to do, or at least run through right now. So go ahead and calculate the formula mass for magnesium carbonate. Here are the molar masses, so they're easy to find. Go ahead and calculate the formula mass now. Please press pause. All right, so we have one magnesium coming in at that 24.31. I have one carbon coming in at 12.01. And I have three oxygens. So I'm going to take that molar mass, I'm going to multiply it by 3 before I add it to the rest. And I'll have a formula mass of 84.32 AMU for magnesium carbonate. So when I go to calculate the molar mass of something, the mass of 1 mole of a pure substance is called the molar mass. So it's the mass of a mole of a pure substance. For example, the molar mass of iron is 55.847 grams per mole. Sorry, my units are down here. My formatting got a little messed up. For example, what's the molar mass of platinum? Okay, you can search your periodic table. You'll find that the molar mass of platinum is 195.08 grams per mole. That means in 1 mole of pure platinum, there are 195.08 grams. All right, so the molar mass, okay, the mass of a mole, depends on the particles that compose the compound. If your element exists as a molecule, okay, as a diatomic molecule, remember Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Remember that Brinkelhoff, the diatomic molecules? 1 mole of these particles contains 2 moles of the element as an atom. Remember, they're called diatomic molecules. So if I'm going to try to determine the molar mass of oxygen molecules, I'm actually trying to calculate the molar mass of O2. So I'm going to take the 16.00 grams per mole that we take from for oxygen from the periodic table. I'm going to multiply it by 2 because there are 2 atoms in 1 molecule. And so the molar mass of oxygen molecules is going to be 32.00 grams per mole. The molar mass of oxygen molecules is twice the molar mass of oxygen atoms. So when we're going to calculate molar mass from compounds, we're going to list the elements. Then we're going to determine how many atoms of each there are. Then we're going to identify the atomic masses from the periodic table. Then multiply how many atoms there are by the respective atomic masses. Lastly, add up the totals for the molar mass. All right, see how we're doing. I'll do 2 of them. See if you guys can do 2 of them on your own. So water, there are 2 hydrogens, each at 1.008 and then there's 1 oxygen coming in at 15.99. I add those up. I come up with 18.006 grams per mole. NaCl, I have 1 sodium coming in at 22.9. Okay, I have 1 chlorine coming in at 35.45. Add those up. I come up with 58.35 grams per mole for NaCl. All right, guys, I want you to try glucose, C6H12O6. Go ahead and press pause now. All right, so we see that there's 6 carbons, 12 hydrogens, 6 oxygens. Make those multiplications and then add up your total for 180.096 grams per mole. All right, guys, try K2O. Go ahead and press pause now. We see that there are 2 potassiums. We see that there's 1 oxygen. Add up those totals for 94.19. Now, the mole is more convenient. It's an amount. Okay, it's an amount of a substance. It's more convenient. The reason we have it is because it's convenient to use as a special counting unit for very large quantities of numbers. Okay, a mole is a unit that contains 6.022 times 10 to the 23rd objects. Okay, objects, anything. We're going to talk about moles of molecules. We're going to talk about moles of atoms. We're going to talk about moles of ions. But it's just any object. There can be a mole of any object. Quite often in chemistry, we use the term particles. Particles is just a generic term for objects. Typically, they're a lot smaller, but those are just a generic name, so don't be fooled by that. It is used due to the extremely small size of atoms, molecules, and ions. Remember that 6.022 times 10 to the 23rd particles being in 1 mole of a substance is called Avogadro's number. So when we look to the periodic table, the average atomic mass is measured in AMU. We're talking about 1 atom, 1 molecule. The weight of 1 mole of an element is measured in grams per mole, right? That's a mole. We have 6.022 times 10 to the 23rd of those things. There's a lot of them. So Avogadro's number provides the connecting relationship between molar masses and atomic masses. So when we go to calculate the number of molecules, let's try this problem. How many molecules of bromine are present in 0.045 moles of bromine gas? Now remember, this is Br2, Brinkelhoff, Br, bromine, so that's going to be Br2. So we've been given 0.045 moles of bromine, and we want to get molecules of a Br2. The connecting relationship is going to be Avogadro's number. So our statement of equality, this should be sounding familiar to you. Our statement of equality is going to be that 1 mole of bromine, Br2, is equal to 6.022 times 10 to the 23rd molecules of Br2. Right? That's our statement of equality. We're going to use these 2 values to actually make our conversion factor. So we have 2 possible conversion factors. We can have molecules over moles. Okay, we can have molecules over moles, or we can have moles over molecules. The values are going to stay the same. They're just going to flip numerator to denominator, depending on what I want to convert out of and what I want to convert into. So I'm going to use this one because I've been given moles of bromine, and so I want moles of bromine on the denominator so that they will cancel out, leaving molecules of bromine as my only unit because that's what I need for my answer. So as I actually go to set up the problem, I'll go 0.045 moles of bromine multiplied by the conversion factor I just selected. I'll see that the moles of bromine cancel out, and I'll have a final answer of 2.7 times 10 to the 23rd molecules of bromine. Again, I know that I want to use this conversion factor because I know I need to have moles of bromine cancel out. And so I simply flip numerator to denominator to make that happen. Now that these 2 values are side by side, I now know, because I've already set up my conversion factor, that I multiply those 2 values. Let's finish up with percent composition. So here I want to calculate the percent composition of magnesium carbonate, the same thing that we did earlier in the slideshow. And so I have the molar mass. I have the molar mass from earlier in the slideshow. It's 84.32 AMU, okay? but I want to figure out what percentage of the entire thing is magnesium. So what I do is I simply take the amount of the compound due to magnesium, which is the 24.31, and I divide it by the total, right? Here's my mass due to magnesium divided by my total mass, and I multiply it by a 100 to yield a percentage. So my percent composition due to magnesium is 28.83%. Do the same thing for carbon. I have one carbon, so it's 12.01 grams due to carbon. I divide that by the total mass of magnesium carbonate, multiply it by 100, I come up with 14.24%. And lastly, I finish up with oxygen. The total is 48 grams, right? 48 due to oxygen because there are 3 oxygens. Divide that by 84.32, multiply by 100. I get 56.93%. All right, and here's the last tip I'll give you in order to make sure that you're doing this correctly. When you add up all of the values, all the percentages, they should add up to or incredibly near 100%. All right, guys, that's it for section 3. I will see you next period.